Alright, hello class. We're back into the second part of this video on, or this lesson on techniques for calculating limits. And as we discussed in the last one, it's essentially whenever you come across 0 over 0 situations with limits, there's always more work to do. Specifically, there's always algebra to do. Okay, and we looked a bit at just the factoring, right? Basic factoring. We looked at conjugating factors. In this video, I want to start with a more advanced example of conjugating factors, but then also show some more of the other algebra techniques you might run into. I do want to preface this by saying that there's a lot of algebra techniques out there, right? You learned a lot of them in your algebra and pre-cal classes. So I can't go over every single possibility, but I can at least hit a few examples of sort of categories, right? Types of things you might see as we go forward. Okay, so we've done your basic factoring guys. We've seen your standard, what do you do when you see a square root guy, and this time I'm going to categorize, okay, what happens when you see fractions or other weird things happening. All right, so let's get into it. All right, let's take a look at this example. Let's say we have the limit as x goes to 3 times x minus 4 times the square root of x plus 5 all over 3 minus the square root of x plus 5. So my advice on all of these is, of course, well, one, start by seeing what happens if you plug things in directly. Notice when we plug the 4 in here, this x minus 4 makes the entire top 0. And we plug 4 into here, this becomes the square root of 9, so 3 minus 3, so this is a 0 over 0 case. It's always a good idea to check to see if that's what's going on before you start like rolling through these, because you might save yourself a lot of time. But of course, in this case, it's a 0 over 0 case. All right, so since I see a square root, I'm going to hit it with a conjugating factor. So now you'll notice we have two square root things here. I did say in the previous video, or the previous part of this video, that you always make your conjugating factor out of the square root term, but we have a square root on the top and the bottom. However, it's the bottom here that is causing the division by 0. This x plus 5 on the top is not really doing anything. All right, so and you need a middle term basically to change what's going on. All right, so we'll do 3 plus square root of x plus 5 on the top and the bottom. Okay, and so we're going to leave the top alone. Oops, I'm using arrows, I don't have to do that. We're going to leave the top alone and have 3 times x minus 4 times the square root of x plus 5 times this thing we just put here. All right, we're not going to touch this. The part that didn't have the conjugating thing, we're not going to worry about. But here, this is a difference of squares. So this is going to be 9 minus x plus 5. Okay, and that is going to give us, okay, the same numerator. I spared you the torment of watching me write all that again, but this 9 minus x plus 5, remember you need to distribute that minus sign. So this will be 9 minus x minus 5, so we'll have, when it's all said and done, 4 minus x. Now, keep in mind, this is almost what we have here, except the signs are different. So what we're going to do is factor out a negative 1. And we could do it here as well, but I'm going to do it down here. Factor out a negative 1. All right, so we get the numerator, we're just leaving alone, all over negative times x minus 4. And if you distribute that negative sign back through, you'll see you get back to that. And now we have that these x minus 4s cancel. We just need to make sure we keep that negative as we go forward. Okay, so this will be now negative 3 times the square root of x plus 5 times 3 plus the square root of x plus 5. And now we should be able to just plug the 4 into it. So we should just get 3 times this will be square root of 9 times 3 plus the square root of 9. And so we will get, this will be negative 9 times 6, right, which will be negative 54. All right, so there's that one done. Bit more complicated, but you know, my advice on these is just, you know, don't try and race to the end. Just take them step at a time. Keep cranking out your algebra until you get rid of that thing, and it's usually something that the denominator needs to cancel. Try and get rid of that, right? You just algebra until you get rid of it. All right, let's look at this example now. Say we're looking at the limit as x goes to negative 1 of 2x minus 1 all squared minus 9 all over x plus 1. Okay, so if we were to just plug in the negative 1 directly, okay, we'd get here negative 2 minus 1 all squared minus 9. So that would be negative 3 squared, so that would be 9 minus 9 all over negative 1 plus 1. So this is a 0 over 0 case. Okay, now, unlike the other ones we've looked at so far, though, the way it's written right now, it's not, you know, it doesn't have a square root, so I don't see the ability to hit it with a conjugating factor, and it doesn't look like it's factorable. I mean, I do have a difference of squares, okay, so we could factor the top that way. It's a little different, okay, but I'm going to show maybe 2 ways to go about this, okay? So first, let's just simplify the top as far as we can. Okay, so we'll FOIL this out. This will be 4x squared, then minus 4x plus 1, then minus 9. Okay, and we'll leave the x plus 1 alone. I know it's tedious, but when you do this, you do need to write out everything. Don't just like write the top over and over and over again. It's really easy to forget that you have a denominator there if you do that. I mean, there are reasons why we are very particular about how things are written. There's a reason for most of it. It's not just us being mean. Okay, so this will simplify to 4x squared minus 4x, and that'll be minus 8 all over x plus 1. And then now we can factor a 4 out of the top and get 4 times x squared minus x minus 2 all over x plus 1. And now we should be able to continue factoring the top because I need 2 things that multiply to give me negative 2 but sum up to give me negative 1. All right, so that should be x minus 2 times x plus 1 all over x plus 1, and there we go. This is exactly what we wanted. We wanted that x plus 1 to cancel away because it's these 2x plus 1s in this that are giving us trouble. Okay, so now we'll just have this 4 times x minus 2, and now we can just plug in that negative 1. Once we get rid of division, or at least x's in the denominator, we shouldn't have any more problems after that. Okay, so this will be 4 times negative 1 minus 2, so that's 4 times negative 3, which will be negative 12. Okay, let's look at this example again, but tackle it in the other way I mentioned, that this is a difference of squares, right? We technically have an a squared minus a b squared, right? The a is 2x minus 1, And the b here is 3, because we could rewrite this 9 as 3 squared. All right, so as I mentioned, knowing the difference of squares is really important because this pattern shows up a lot, and knowing it can actually save us a lot of time, because here, recognizing that this was a difference of squares jumps me straight to the limit, and don't need to write that, that's just habit. That just lets me go straight to, remember, it's a minus b times a plus b. Okay, so my a is 2x minus 1 minus b, which is 3, times a, which is 2x minus 1, plus b, which is 3, all over x plus 1. Then we get 2x minus 4 times 2x plus 2. Okay. Now you'll notice that we can factor 2's out of both of these. So we'll go ahead and do that. We factor a 2 out of this, and we'll get x minus 2. We'll factor a 2 out of this, and we'll get x plus 1. And so the x plus 1's cancel, and you'll notice if I take these 2's and bring them together, we get 4 times x minus 2. This is exactly what we got last time. All right, so this will be 4 times negative 1 minus 2. That's 4 times negative 3, which will be negative 12, and we're good. Which way is the correct way? The thing that you're going to notice about calculus is there are multiple ways to get to the same place many times. Okay. And as long as every step that you take is correct, you're going to get to the same answer. And this is both a blessing and a curse, because it does open you up to have some creativity on how you get from point A to point B, but that also means it's tougher for me to just say do this and you'll get it, right? And instead I have to say, well, we're going to fall back on our algebra to get us there. Okay? All right, let's look at some more examples. All right, here's another example that students tend to love. It's when we have fractions within fractions. Okay, but it's not maybe as difficult as you might think, because, all right, yes, when we plug in the 0, we're going to get 1/5 minus 1/5, 0 over 0. This is definitely a 0 over 0 case. Okay, so what do? Well, here is my suggestion for fractions that you don't like, but there are other ways you could go about it too. Okay, so I'll show, just like last time, I'll show the 2 ways we can go about doing it. My preferred way is I take all the denominators that I don't like and multiply by them. Oh, okay. What do we mean by that? Well, here I have one fraction that has a denominator of 5 plus h, and here I have one with a denominator 5. So what I'm going to do is just like maybe not just like, but very similar to the conjugating factor idea. I'm going to take the 5 and the 5 plus h and multiply the top and the bottom by this value. So it's not exactly a conjugating factor, but it is going to simplify this fraction within a fraction thing, because when we distribute this 5 times 5 plus h, it's going to cancel out our fractions. Okay, so I'm going to write it in a long way, but in practice I don't usually do this. I usually just go to the canceled version, but I'll have 1 over 5 plus h times 5 plus h. And then I'll have minus 1 over 5 times this 5 times 5 plus h. And this whole thing is over now h times 5 plus h. Now, don't start canceling these things. All right, that's just going to get you right back to where you started. You don't want that. I know it feels good to cancel, right? We love canceling, but we're not going to cancel across the fractions. What we're going to do instead is cancel on more micro level. Because here I have the 1 over 5 plus h, so these 5 plus h's cancel. And here I have the 1 over 5 times 5 plus h. Here it's the 5 that cancel. And I'm going to leave the denominator alone. Okay, so let's redo that. All right, so what we end up with is, well, all this just becomes 5. All this just becomes 5 plus h. Be real careful that you leave the parentheses. We have that minus here. That minus needs to distribute across. Okay. Then, here in the denominator, I'll just leave this as, I'll write it as 5h times 5 plus h. Okay, now don't cancel this 5 plus h. For one, you can't do it like that, and two, just don't. What we're going to do is continue simplifying the top as far as we can. So we'll get 5 minus h. Remember to distribute that minus sign. And this will be all over 5h times 5 plus h. Now the 5's cancel and the h's cancel. However, I don't recommend doing this all in one step. I see a lot of mistakes when students do that. Just go ahead and write your next step. It's not a race. Okay. Now I'll cancel the h's, because a lot of times what happens is when people cancel all this, they forget that there's going to be a -1 out here. All right, this will be -1 over 5 times 5 plus h. Okay, and now we should be able to plug in the 0, because when we plug in the 0, we're going to get -1 over 5 times 5 plus 0, which will be -1 over 25, and there we go. Okay, that's the first way I recommend doing this particular problem. All right, what's the second way? Well, the second way is you can just do the fraction arithmetic. Okay, so there are a lot of ways you can do that, but I find the quickest way is to take one denominator and move it up here, another denominator and move it up here, and then multiply the two denominators together. Okay, so this will end up being 5 minus 5 plus h all over 5 plus h times 5. All over h. Now here's the part where we need to turn this into fraction division, because we have our main fraction bar right here. We have a fraction in the numerator, and technically we have a fraction in the denominator because this is h over 1. Okay, and so when we divide one fraction by another, we flip it and multiply. Okay, so this is going to be 5 minus 5 plus h all over 5 plus h times 5. And actually, in this step, I'm also going to go ahead and simplify the numerator while I'm here to give me 5 minus h. Okay, and then this 1 over h, when we flip it over, I just said it, actually, this h over 1, when we flip it over, is 1 over h. And you should notice that this is exactly what we got last time, right? This becomes negative h over, oh, I left out a 5 there, sorry about that, over 5 plus h times 5 times 1 over h, and the h's cancel. And we get -1 over 5 plus h times 5, which will come out to be -1/25 again. Okay, so we'll get to the same place. It's just more about what you're more comfortable with. I prefer this method where I just multiply. It looks like it's more steps, but usually I don't write this particular step here. I just know what I'll be canceling. But, you know, which one is worse? Well, as far as I'm concerned, it's probably it satisfies the law of conservation of misery, right? It's about the same amount of work, same amount of hassle each way you go. It's hard to avoid the work when it comes to problems like this. All right, let's look at this new example here. Let's say we have the limit as w goes to 1 of 1 over w squared minus w minus 1 over w. Okay. All right, so this is a limit with fractions in it, but it's not quite a 0 over 0 case, is it? Because when we plug in the 1, we get 1 over 0 minus 1 over 0. This isn't quite a 0 over 0 case. In the next section, we'll talk more about this in greater detail, this 1 over 0, and how what we're looking at here is actually going to be an indeterminate form. So in the meantime, though, let's do some algebra and then see, what we can do with it. And I'm going to start by factoring the denominator here. So let's factor this denominator. We can factor a w out of it. So we'll get 1 over w times w minus 1. Okay, all over, or minus 1 over w minus 1. All right. So I see something here. I see we almost have a common denominator. We just need, well, a w here because we have the w minus 1. We just need the w. So I'm going to multiply the top and the bottom by w, and that's going to give us a common denominator. Right? So this will lead us to a 1 over w times w minus 1 minus w over w times w minus 1. Right? And now we get 1 minus w over w times w minus 1. All right, now we have an indeterminate form we're familiar with. This is now a 0 over 0 case because if we try to plug the 1 in directly, we'll get 1 minus 1 and then a 1 minus 1 here. So this is now a 0 over 0 case. It didn't look like it at first, right? At first it was a 1 over 0 minus 1 over 0 case, which we hadn't really come across before. But with a little manipulation, now it's a 0 over 0 case. However, we've done most of the work we need to do. All we really need to do at this point is factor out a negative 1 from somewhere. I'll do it from up top. Because if we factor the 1 out, you'll notice I have a 1 minus w and a w minus 1. So when we factor out the negative, right, the numerator becomes a w minus 1. So we get negative w minus 1 all over w times w minus 1. Now the w minus 1's cancel. And we're left with negative 1 over w. And now we can just plug the 1 in. All right, we'll get negative 1 over 1, which is negative 1. All right, for this next example, let's look at the limit as x goes to 0 of x minus cosine, 1 minus cosine x all over cosine squared minus 3 cosine x plus 2. All right, I know a lot of students sort of freak out a bit when trig shows up. I don't want to say it's natural to have your brain shut off when you see these trig functions. But what I will say is a little tough love here. It's probably time to get over it. Remember, cosine, sine, tangent, all those guys, they're just functions. Okay, they're just functions. They just have a different behavior than, say, the x squareds and the square root of x's and stuff than we're used to. Okay, but don't start freaking out when you start seeing trig functions. Just approach it like you normally would. So here, we have this guy, if we plug in the 0, well, cosine of 0 is 1. So I can already see the potential for problems here, because when we plug in this 0, we're going to get 1 minus 1. So we get 0 on the top, and then here we'll get 1 squared minus 3 plus 2. Oh, that's a 0 over 0 case. Okay, so that means we have some work to do. Now, what can we do? Well, all we have right now is algebra. Right? It's the only course of action we have for 0 over 0 indeterminate forms. Now, the main one we've been looking at has been factoring. Now, I submit to you that this can actually be factored here on the denominator. Imagine it like this. Let's let y equal cosine x. Okay, so if we let y equal cosine x, then cosine, I'll write it here, then cosine squared x minus 3 cosine x plus 2 is equal to, well, I could replace cosine squared x with y squared. I could replace 3 cosine x with 3y, and I could replace, well, the 2 with just the 2. And now, just looking at this, we can see that this factors, right? We need factors of 2 that will sum up to be negative 3. It looks like it's going to be y minus 2 times y minus 1. Right, the negative 2 times the negative 1 is 2. The negative 2 plus the negative 1 is negative 3. Okay, so if it's with variables, it's no problem. It's when it's with cosine and whatnot that people start to freak out, but let me be careful with that so you don't think it's a fraction. So if I just put the cosines back in now, say cosine of x minus 2 times cosine of x minus 1, hopefully you can kind of see how we're going to approach this. Okay, because this now can factor into, I'll leave the numerator alone, but now the denominator becomes, I can factor this as cosine x minus 2 times cosine x minus 1. And these are almost the same except for a sign. And when they're almost the same except for a sign, the trick is always to factor out a negative. And then you can swap the signs when you do that. You're going to see that trick a lot, so get used to it. All right, so now we're left with negative all of cosine x minus 1 all over cosine x minus 2 times cosine x minus 1. Now those cosine x minus 1s cancel nicely, and we're left with negative 1 over cosine x minus 2. And now we should be able to just plug the 0 in and get negative 1 over cosine of 0 minus 2. This is just a 1, so we get negative 1 over negative 1, which is 1. Okay, so be on the lookout for things you can factor that are not actually x's or y's or u's. You can factor things with cosines or sines or tangents or natural logs or e to the stuff. Okay, that is that is not going to, or that shouldn't have to stop you. Okay, next up, let's talk about working with absolute values. Absolute values are an interesting thing that can pop up from time to time. So if, let's say, we had this limit, the limit as x goes to 0 from the left of x squared minus x all over the absolute value of x. Okay, now to deal with this, So if you were to just plug the 0 in, you'd get 0 over 0. So your first thought might be, okay, this will be, let me just factor the top. That'll be x times x minus 1 all over the absolute value of x. Now, does x and the absolute value of x cancel? That is a really interesting question. So let's remember what the absolute value does. The absolute value of x can be defined as a piecewise function. Okay? Basically, it doesn't do anything if x is greater than or equal to 0. Right? If it's positive, the absolute value doesn't really do anything. If it's negative, well, that's when it changes things. At 0, it doesn't really do anything. So if we give it a positive x or 0, it doesn't do anything. On the other hand, if x is negative, it negates x. Right? Because if I give it a negative 5, it gives me negative 5, which is positive 5. Okay? So, how we use absolute values when we're talking about limits is in basically using this. So x going to 0 from the negative side, remember that is x less than 0. Right? So we're going to use the less than 0 case here. Right? So this is going to be x times x minus 1 all over negative x. And this comes from the fact, well, it comes from here. It comes from the absolute value, right? Since x is negative when we're checking the limit from the left. Okay? So now these x's can cancel, and we're left with a negative on the bottom here. So this will be x minus 1 all over negative 1, and now we can just plug in the 0. Let me shift over here. Now we can plug in the 0 and get 0 minus 1 all over negative 1. Negative 1 over negative 1 is 1. Okay? What happens if we check this limit from the right side? Okay, so we have the first initial step, right? We factor the top. But now, instead of the absolute value becoming a negative x, it's going to just stay as x. Because in this case, right, when x goes to 0 from the right, here we're talking about x being, well, not equal to, but strictly greater than 0. So we get positive x, or really just x left alone, because x is positive in this case. So now these x's cancel, and we get just x minus 1, which we can plug the 0 into, and we get negative 1. Well, the limit on this side was positive 1, and the limit on this side is negative 1. So that means that the two-sided limit of this function does not exist. Right? There is a jump in the graph of this function. In fact, if I graph this function with some software, we see the jump right here. Okay? Which we saw with analytically with the limit. Okay, but here's a nice graphical representation of what's happening here. So this little function here, this little absolute value of x over x, or x over the absolute value of x, this guy here, this has its own sort of definition. We can think of it either way, really. Because when x is positive, we get x over x when x is greater than or equal to 0. And really, it can't be equal to 0 because we'll get 0 over 0. And then when x is negative, we get x over negative x, or just negative x over x when x is negative. So this actually ends up being simply 1 when x is positive and negative 1 when x is negative. All right, so if we were to graph that, I don't really need software to graph that. To the right, we'll have an open hole or open dot, and another open dot, and here we go. Okay, so this is the graph of absolute value of x over x, or flipped around. That part doesn't really matter. It's going to be the same either way. So when you see those things start showing up in your limits, like an x over absolute value of x, keep in mind that something like this may be happening. Right? You got to be really careful and vigilant about that. All right, now this is a great segue into working with piecewise functions. Since the absolute value was given in pieces, when we approach limits on a piecewise function, what we're basically trying to do is just figure out, is there a jump there or not? Is there a jump? What are the limits from either side? Okay, so just to give you an example, okay, let's take this pretty crazy piecewise function here. It's going to be 0 when x is less than or equal to negative 5. It's going to be the square root of 25 minus x squared when it's between negative 5 and 5, and 3x when x is greater than or equal to 5. Now, here's the thing. I'm a very visual learner myself. So what I do is, you don't even have to graph the function itself. I like to graph the pieces of the function. So I would say, okay, over here, from negative 5 back, right, and including negative 5, we have the 0 piece. Okay. From negative 5 to 5, now notice how I'm drawing this. I'm showing that I have an open dot to open dot. This is the square root of 25 minus x squared piece. And then from 5 on, okay, I have the 3x piece. So I have basically broke this down into the orange piece, the pink piece, and the green piece. Okay, so if I'm asked about limits regarding this particular function, I like to think of it broken down visually like this. Again, I don't care what this really looks like on a graph right now, but if I was asked, like, okay, what's the limit as x goes to 0 of f of x? Well, this is a two-sided limit. So I need to check, oh, sorry, not 0, but let's do negative 5. Okay, negative 5. So this is a two-sided limit. So I need to check from this side and from this side to make sure that they match. Okay, so I'm going to start from the left. So I will try to color match this as the limit as x goes to negative 5 from the negative side of f of x. That's going to be the orange piece, right? And so that is going to be 0 because that function is just 0. All right. Now, when I look at the limit as x goes to negative 5 from the right, the positive side, okay, I am going to now look at this pink piece, the square root of 25 minus x squared. And now that's where I'm going to put the negative 5. So this will be negative 5 squared minus, whoops, did that in the wrong order, didn't I? Sorry, it'd be 25 minus negative 5 squared. Oh, that's 25 minus 25, that's 0. Oh, these two guys match, so we get 0. Okay. And it turns out that f of 0, well, the equality happens here in the orange piece, so that's actually from the orange piece as well, the 0. Okay. Now let's look at the limit as x goes to positive 5. Once again, this is a two-sided limit, so I'm going to check from the left side. So this would be x going to 5 from the left, and here in the green will give me x going to 5 from the right. All right, so we'll check the middle pink portion first. So the limit as x goes to positive 5 from the negative side of f of x, again, we're using the square root piece. It will be 25 minus 5 squared, all square root. So that's 25 minus 25 in there, so it's 0 again. And then we're going to use the green portion to find the limit as x goes to 5 from the right of f of x, and that is the 3x. So we can just plug the 5 into the 3 and get 15. Ah, these don't match, so this does not exist. So that tells me that there's no jump here. The limit as x goes to negative 5 of f of x is 0. No jump. And we're continuous because there's no hole there, but here there will be a jump. Okay, so we can find out a lot without even looking at a graph. Now, of course, we can look at the graph. Here's that orange piece, that's 0 up to negative 5. Here's that square root of 25 minus x squared here, that's a semicircle, and then it jumps up to this line, which is 3x. Okay, so yeah, we can see that it's nice and continuous here, the limit exists, and the function's continuous, but we have a jump here. Okay, and this is, like I said, we don't even need to know what the graph looks like. We can just split it up into pieces and come at it from the different directions and see what's going on. All right, so the last thing we need to talk about in this particular lesson is what's called the squeeze theorem. And the squeeze theorem basically says that if you have three functions, all right, let's say f of x, g of x, and h of x, where let's say f of x is less than or equal to g of x, which is less than or equal to h of x. So g of x is trapped between f of x and h of x. Let's say for all values of x near a. So it doesn't have to be everywhere, but everywhere near a. And if the limit of f as x goes to a is, say, L, and the limit as x goes to a of h, h of x is L, then the limit as x goes to a of g of x must also be equal to L. Okay, so let's think about what this is actually telling us. This is telling us that if g is trapped between these two functions, and at a these two guys have the same limit, then g must also have the same limit. To explain this on a graph, if you imagine, okay, that we have let's say we have f of x does this, and let's say, so that's our f of x, and let's say this is our a value, right, which would make this, let's say, L. All right, and let's say h, I don't know, it does something like this, and it comes up and it has the same limit at a that f does, right? They have the same limit. They both have the limit of L here at a. And specifically, we know that g of x is trapped between these two for all values near a. So g, well, the only way that can happen is if it gets squished in between these. Okay? And if it's squished in between these, then it must also have the same limit. So g of x also goes to L. Right? So that's what the squeeze theorem gives us. Now, where the squeeze theorem is useful are trig type things. All right, so for example, let's say we're trying to find the limit as x goes to 0 of x squared times sine of 1 over x. Now, we've looked at this sine or cosine of 1 over x. We know that that limit doesn't exist at 0. However, what about when we multiply by x squared, or something that goes to 0 at 0? So here's the idea. The sine part we know does not exist as x goes to 0. Okay? However, we know it oscillates between -1 and 1. Right? That's just, it's sine of whatever. We know that goes back and forth. We looked at that earlier. But this guy, the x squared, goes to 0 as x goes to 0. So which one's going to win out? Which one will win? Okay, we can answer this with the squeeze theorem, because for all x, right, sine of 1 over x is trapped between -1 and 1, right? And this should, for all x not equal to 0, since we can't plug 0 in. But for pretty much every other x, -1 is less than or equal sine of whatever less than or equal to 1. Now, multiply both sides by x squared. And when we do that, we'll get, I said both sides, multiply all sides by x squared. We'll get -x squared is less than or equal to x squared times sine of 1 over x, which will be less than or equal to x squared. Okay? Now, take the limit as x goes to 0 of everything. All right, so we'll have the limit as x goes to 0 of -x squared, the limit as x goes to 0 of x squared times sine of 1 over x, less than or equal to the limit as x goes to 0 of x squared. Well, -x squared and x squared, we can take those limits pretty easily. They both go to 0, right? Because we can just plug in the 0. So we get that 0 is less than or equal to the limit as x goes to 0 of x squared times sine of 1 over x, which is less than or equal to 0. Oh, so the limit as x goes to 0 of x squared times sine of 1 over x is equal to 0. Okay, to view it on the graph, you'll notice I'm very zoomed in here, but here is x squared, here's -x squared, and here is the x squared sine of 1 over x. Okay, so as we can see, that sine, or x squared, sine of 1 over x is always trapped between the x squared and the negative x squared. So that squeezes it down to have the same limit. All right, so that should about do it for this particular lesson. Like I said, there are way more examples than I could ever do, way more situations, different types of ways to approach this. But this should hopefully give you an overview of the different categories you might run into when trying to evaluate limits by hand. Okay, so I will catch you all on the next one when we start looking more closely at the constant over zero case. And the next one, I'll see you all then. Cheers.